for you, and also it can be stored to me. But remember that please do not absent just considering that the lecture will be recorded, because your attendance will be your participation points. Okay, so take it seriously. Okay, and actually I need to do some more settings, like I need to be to the default participation, otherwise I have to do manually every student. Anyway, let's go on. So we already know what is alkene, what type of reaction, and what type of hydrocarbon it is. Now we can see here the one of the example of alkene in our human bodies, that you can see the femoral component polyethylene bearing and the tibial plate. Actually, the polyethylene is famous for using as a self-lubricating surface of movement of metal part of the knee replacement. So if somebody having a trouble and need artificial knee replacement, this alkene plays a crucial role as a lubricating, self-lubricating surface, so that the metal can move flexible like our natural knee parts. And also this is very useful because it doesn't have any side effect or foreign body reaction. Sorry. Now, okay. Now the reactivity of carbon double bond. Actually, carbon-carbon double bond here, the main reason of lots of chemical reaction, as you already know about the pi bond that have with the carbon-carbon double bond. One is pi bond and one is sigma bond. Actually, pi bond is formed because of the unhybridization, unhybridized orbital, and those are very loosely bound bond. As a result, that's very easy to break, and that's why lots of chemical reaction happen. And one of them is catalytic hydrogenation. During the catalytic hydrogenation, actually they break the carbon-carbon pi bond and the hydrogen-hydrogen sigma bond and produce the two, you can see here, two carbon-hydrogen sigma bonds with lots of energy. And the product formed with the two carbon-hydrogen, that's eventually more strong than the reagents. As you know, the sigma bonds are strong than the pi bond. So this is the carbon-carbon double bond reactivity. Now, types of alkene reaction. So mainly the addition, also we will see elimination kind and substitution kinds of reaction. Bonding of alkene, we already talked in the last class that the electrons in pi bond are loosely bound and the double bond, let's use now. I mean, if I use the laser points, somehow it's not let me work in other places. But anyway, I think everybody joined now. So the double bond acts as a nucleophile attacking electrophile species. So first double bond work as a nucleophile and they have a tendency to attack nucleophile. When the pi bond break and some proton will come to that and another, and then after protonation the carbocation will form. Now carbocation is protonated carbon, which we call the nucleophile. Nucleophile means they are molecules that are electron rich and they can donate a pair of electron to electrophile. As we know, the electrophile, that means electron loving. So when the bond break, bond try to break, Why break? Because pi bonds are loosely bound, and when they see some electrophilic species, they try to break and they try to bond with those electrophilic species. So as a result, the carbocation form, and when the carbocation form plus positively charged carbon, here you can see, and this is actually deficient of electron, and that's why this carbocation look for the electron, and nucleophile having a extra addition, a pair of electron, they can donate. As a result, this carbocation in the second step of the addition reaction, and they make a bond with the nucleophile. So first step, the breaking of pi bond, and then protonation, and then second step, the carbocation will form, which are electron deficient, and they will look for electron. So which species having an electron, extra electron or pair of electron that can donate to this carbocation? Nucleophiles. And nucleophiles are those molecules which are electron rich and can donate a pair of electron. Okay, and normally nucleophile are base and electrophile are Lewis acid. So now you can see here the mechanism of electrophilic addition. Here pi electron attacks the electrophile. When pi electron attacks the electrophile, then what happens? Then this bond break. When this pi bond is break, then the carbocation is formed and another carbon is try to make a bond to some proton. And here you could see the electrophile or some positive charge make a bond and leave this carbon with the electron deficient. That's why this is positive carbon called the carbocation. In the second step, nucleophile attacks the carbocation because nucleophile can donate, have excess electron, and the carbocation having a deficient of electron. As a result, they are very compatible to bind a new bond, and this type of addition happens. I hope you understand here. Do you have any question here? Okay, let's see some example here that what type of additions like hydrogenation, halohydrin, we will go one by one. So here just the summarize. So when I will explain one by one, you will find all that example. So like hydrohalide, like hydrogen chloride, or hydrochloric acid, hydrobromic acid, those type of addition, oxidative cleavage and apooxidation. This all about actually our discussion. I also would like to remember you that in our course, according to our syllabus, we will be focusing on chemistry of the chemical reaction of the hydrocarbon, as I can see by studying the alkene. So you guys really need to focus and do the practice, okay? And that's why I would happy to record the lecture, okay? So first of all, we are going to see the addition of hydrogen halide to alkene. So if you understand the mechanism, and this mechanism actually follow the Markovnikov addition or Markovnikov rules. So when now we will be going one by one addition example and see the mechanism, that will be more clear and make sense to you, I think. So first of all, we have the addition of hydrohalide to alkene. You can see according to the syllabus, I also marked the section so that it can be easy for you to follow the syllabus and study when you use the book, textbook. Step 1 is the protonation of the double bond. This is the same that step 1 is here, okay? Now, the protonation step forms the most stable carbocation. So, protonation step Here, pi bond break because pi bond are very loosely bound and they look for some electrophile. So that's why a proton or electrophile bind here and leave the carbon which have a electron deficient as a positive carbon. This is called the carbocation. In step 2, the nucleophile attacks the carbocation forming an alkyl halide. So now hydrogen bromide, hydrogen chloride, hydrogen iodide can be added through this reaction. See here. Now if you look into here, we can see the example of this alkene. If you see here, 1, 2, 3, 4, this is butene, correct? So here we go, the double bond CC, this is we call the carbon-carbon double bond or main functional group of attacking the pi bond because of their loose binding. Here what happened, this HBr as here when the any kind of chemical reaction occurs, couple of things happens. We saw the reactants and we saw the product. Actually in between couple of things happen. What happens? We need to break the old bond and we need to form the new bond, correct? So here not only the alkene bond breaking, if the alkene bond break here, pi bond, that means this double bond carbon will attach to electrophile. Here also we need to break the bond, correct? So what happened when this pi loosely pi bond to break and they try to make a bond with the hydrogen. In this time, this bond, hydrogen and bromide, this bond is break. Now, what happened here? Bromine is very highly electronegative. Highly electronegative. That means I hope that you little bit of study on that. That they having a tendency. They having a tendency to attract electron toward them. And since this is bromine is highly electronegative, when this hydrogen bromide bond will be breaking, so this bromide ion will pull the electron towards it. That's why here you could see that extra lone pair electron, and this bromide ion will act as a nucleophile. Got it? And this is a base. So when this bond will be breaking, so then it will this bromide ion with the excess pair of lone pair will be acting as a leaving group or nucleophile. And here the hydrogen will be attached to the carbon. Now the thing is that we have the two types of bond break. If anybody remember or even don't remember, we discussed in the alkene chapter section 8.7 that homolytic cleavage and heterolytic cleavage. Homolytic cleavage, when a bond breaking happen and the electron distribution go equally to both species, and heterolytic cleavage when highly electronegative species will take more pair of electron or unequal distribution. So that means if you are highly electronegative, that means you have a more muscle power, if we can just say like that. So this is the reason here the heterolytic cleavage and it leaves. So this is how actually the mechanism works for the addition. Second step, this nucleophile attack the carbocation and this bond, the new bond formation, and this product will formed. Do you have any question here? Okay, so now we will move on. The Markovnikov rule. I have to tell one more thing. I have already described the most important two part and the last part. Now, Markovnikov rule. Whatever the addition now I have discussed that follow Markovnikov rule. Now what is the Markovnikov rule according to our textbook? The addition of a proton to the double bond of alkene result in a product with the acidic proton bonded to the carbon atom that already holds the greater number of hydrogen. Now let's go back to, I want to make it easy, the rules. The rules is that this is actually, if you consider from both sides, it is the same. But normally, do you guys remember the 1 degree carbon, secondary, primary carbon, secondary carbon, or tertiary carbon? Let's write here. So 1 degree carbon, when carbon attached to just one carbon and it has more hydrogen. 2 degree secondary carbon, when carbon attached to 2 carbon. Tertiary carbon, when carbon attached to 3 carbon. So actually, the more substituent the carbon to, that can form the more stable carbocation. And the primary, that means less carbon and more hydrogen. So according to our Markovnikov rule, try to be understand that they are telling that this proton part will add after breaking the pi bond to those carbon which have more hydrogen. That means that when we will see any kind of alkene for our reaction, we will find the double bond and the carbon which have the less stable. That means we have to find the carbon that which is primary, secondary, or tertiary. If the primary, then hydrogen will add to the primary and secondary carbon will make the carbocation. If you have the carbon-carbon double bond that is between secondary and tertiary, then secondary carbon will add the hydrogen and tertiary will go to the nucleophile or the base or bromide, like that. So this is the thing you need to be understand. Otherwise, you guys will be mess up that where I will add hydrogen and where. Actually, this is the most important rules in this section, because we will see the Markovnikov rule. In the same time, we will see the anti-Markovnikov rule. So if you don't understand these three things, it will make you challenging. But if you are clear in the beginning, this couple of things now I am describing, it will come repeat and repeat with some additional new information. So I hope that you guys got it. So according to our rule, there are three things. First of all, protonation of the double bond. Pi bond will be break and proton will go to the carbon which is attached to more hydrogen or less stable like primary. And carbocation will form to those carbon which have a higher stability like secondary carbon or tertiary carbon. Okay, and when the proton will be add to the first step, the second step will be the nucleophile attack with the carbocation, because carbocation having a deficient of electron, that's why this is called the electrophile. So if I have a deficient of electron, I will look into electron. So nucleophile, this is the Lewis base. Actually, those molecules or species act as a nucleophile having the pair of electron to donate. That's why they are very compatible to making a bond. Hope you got it, the things. And this is the Markovnikov rule. So the Markovnikov rule's second part or extended part is that in an electrophilic addition to the alkene, the electrophile acts in such a way that it generates the most stable intermediate. So we have to remember those things to find out that which carbon will be suitable for protonation and which carbon will make most stable carbon. Remember, the carbon with more substituent will able to make the more stable carbocation. So this is the example, and I think now we can, if we look into here, we can see here, if we look into carbon, see here, this carbon, and also here carbon. So it seems this is the most stable, like tertiary, than this carbon. Correct? Because this carbon have the one hydrogen secondary. So obviously this carbon will be the target for the protonation, and this tertiary will be the carbocation according to our Markovnikov rule and the addition rule here. But if you do like that, this is not the correct one, because we already find the two rules is here. The protonation, see, the product with the acidic proton bonded to carbon atom that already held the greater number of hydrogen. So if you see, here is a hydrogen more, and compared to here, because this is the tertiary. And second portion, we saw according to our rule that the electrophile acts in such a way that it generates the most stable intermediate, carbocation. So here we go. Sorry, this is not, here we go. Okay, so this is the important things. If you are clear, this chapter will not tough to you. Again, you can, this is the second part of the mechanism. Oh, I can see some student. I'm sorry, I was focusing here, so okay. Sorry, here. Sorry. Just a minute. Since I'm doing presentation, I don't know why I could not see my chat box. So if you have any question, you are all unmute. So you can ask me, okay? Yeah. Now, the reaction energy diagram. See, what we have just described here, you can able to see here. So, okay, this week I will figure it out how I can set it as a default so that I don't need to manually allow you to let in here. So this is the alkene. As you can see here, the alkene, this side has a more hydrogen and this side has a more methyl, carbon. So obviously this will be target for the protonation, and here will be the stable carbocation, and we can now see here the blue, the if the form is here, this is not the correct one according to our Markovnikov rule. But when the hydrogen or protonation will be here and this carbon will make the protonation, that it will be secondary and more stable carbocation, which will ultimately bound to the nucleophile bromide. And actually, this is the major product of the reaction. However, when we do the laboratory synthesis, sometimes this type of minor product, a less stable product, is also produced, but this is negligible. So this is our correct answer, what we just explained. And this is actually the Markovnikov rules. Now, here we can see the another example. You remember that when we name the alkene, we know that when the cyclic alkene, we don't need, we start always from the beginning, like where we will see the double bond, we will say this is 1 or this is 2, like that. So now we will do the same addition reaction. This is another example. Here, if we consider the carbon, and here is another carbon, and this is the double bond. So in that case, this carbon having a hydrogen, but this carbon having a methyl. So obviously here the protonation will happen, and here the carbocation will, this place is formed, and here the nucleophile atom nucleophilic attack will happen because carbocation having an electron deficient. So carbocation will find a pair of electron from here. And you remember that when this bond was breaking, due to the higher electronegativity, bromide pull all the electron that was used to make the hydrogen bromide bond. As a result, the bromide having this extra lone pair electron and work or serve as a nucleophile, so that the next step, this bromide can give this lone pair electron to the carbocation. And similarly, this is not the correct one. And another example, look into here. I already mentioned the another example. So you can see here. So you don't need to be worried about what type of compound, but if you see the double bond and if you can find out the carbon and what type of substituents, then you have to follow the rule and you have to proceed on. I hope that you are very clear now about our addition and Markovnikov rule and extended rules. See the mechanism. Same. I mean, if I now ask you to write the mechanism, I think you guys can write the mechanism now. You don't need to be even take help from me. And this is the similar mechanism that we explain. And you will look the carbon to secondary, tertiary. I also make when I was little bit of studying here for your lecture. So you can see that how it works. And there are a couple of examples here. Now, while we have a rule, when we study chemistry, we always have exception or the anti, correct? Like in this society, if we have a hero, we have an anti-hero, correct? This is very natural. So also we need this. We need everything in the, because if we have day, we have night. Without night, we cannot able to find the significance of day. Similarly, for our need, sometimes anti-Markovnikov product is also necessary, and anti-Markovnikov product can be produced in the when we proceed the chemical reaction in the presence of peroxide. So then this is also called the free radical addition of hydrogen bromide. Actually, what is the difference that from the previous, the Markovnikov addition of alkene? Let's see here. In the presence of peroxide, hydrogen bromides adds to an alkene to form the anti-Markovnikov product. Peroxide produce free radicals. Why? Because when I talk about the homolytic bond cleavage and heterolytic. We saw till now the heterocyclic because nucleophile due to the high electronegativity, bromide pulled all the pair of electron that was used to making a bond. Here we will see the different thing. Here we will see the homolytic cleavage because of the presence of this peroxide. As a result, when the bond will when the bond will break, they will have the equal distribution of electron, and which will ultimately produce the free radical, and that will make the anti-Markovnikov addition. Anti-Markovnikov addition means just a flip of the Markovnikov addition. So now you can ask me, Professor, when we will do example during our exam, so how we will differentiate that this example will follow the Markovnikov rule or anti-Markovnikov? You will find in the presence or absence of peroxide. If you see the reaction is regular, you will not find any peroxide. But when you will see the sentence or reaction that in the presence of peroxide, you will make sure that it will be free radical addition and it will follow the kind of anti-Markovnikov rules. So what happened in the mechanism? So when the reaction starts, so first the peroxide bond breaks homolytically, as I just mentioned, to form the free radical of, this is actually fast radical or free radical, because this is, lone pair is divided due to the equal distribution of the electron when this bond is breaking. As a result, we have this free radical. And then this hydrogen is abstracted from hydrogen bromide. What happened then? Since the free radical is happening here, the bromide is going to the just flip the less carbon, less stable carbon, because here the carbocation doesn't form, here the free radical form. This is the difference. So as a result, the bromine adds to double bond, forming the most stable radical possible. So here the bromine will add to the less stable carbon, because here the scenario is different. Here we need to produce the more stable radical. Now you tell me why? Because this is very natural. If the carbon atom is more substituent, that means these are more stable and can make the free radical more faster. As a result, the bromine go to here. Not the hydrogen. Okay, and this is the difference between the Markovnikov addition and the free radical addition. As a result, the methyl, here you could see the product go the upside, flip. In the Markovnikov, we saw the hydrogen or proton add to the carbon which have more hydrogen or less stable. But here we see the flip. Why? Because here we need to produce the free radical carbon stable, and free radical carbon makes faster with the stable carbon. Stable carbon means our ratio here like that. Okay, I can write it down. Like let's take the pen, like the stability of carbon, like 3rd degree, 2nd degree, and primary. So the more faster free radical will form tertiary, then secondary, then primary. And this is the reason here the free radical form, and that's why bromine add here. And second step, the hydrogen will be add here. Okay, so this will be the correct product in case of free radical addition, and this is also kind of anti-Markovnikov rules. See, anti-Markovnikov stereochemistry. So you can see here the free radical will form here. Another example is here, because this is the more stable, and this free radical form faster than this carbon, and this is how it works. Okay, the intermediate tertiary radical forms faster because it is more stable. Hope you got it. Here is some example. You can find it down, and remember that when mainly this type of addition happen in the presence of peroxide. Actually, this is the addition, and same kind of addition we can do in acidic, in the presence of acid. So this is the another example, another way to make the same product, similar product. Okay, so that's why I write here the another way. Okay. Now hydration of alkene addition of we also say in the textbook, if you see the headline, you will see the addition of water. See, or hydration of alkene. Addition of water means here we will have the pattern is same. Okay, that's I was telling that my intention was to make you clear the rules, then you will automatically find it, just the difference. So what you have to do, you have to practice with your notebook. Okay, because once I do the lecture, you know that what is going on. Then if you do the practice, then you will be very familiar the kinds of reaction in every chapter. Okay, so here the thing is that it will follow the Markovnikov addition. So Markovnikov rules or addition the same. So first will be the protonation, and second will be the nucleophilic attack to carbocation. So here what will happen? Addition of water to the double bond forms and finally alcohol, because this will come. See, this will come. So this is the reverse of dehydration of alcohol. Yeah, and also we did the same reaction in the last semester. The thing is that last semester we had so many general chemistry. I saw that some students are not so focusing into the end chapter or something organic, but if you focusing, I think you remember. So we did, this is the reverse of, reverse means this is the kind of reverse reaction. So we did the from here to here, alkane to alkene, and here we are doing alkene to alkane, alcohol to alkene we did in the last chapter, in last semester, and now we are doing alkene to alcohol, and this is also addition of water or hydration of alkene, the reaction, and this is the same mechanism. See, same thing will happen, and normally what happened here, don't be confused. You know, there you can see the hydronium ion. Actually, this is and what are the same. Okay, don't be how to say, don't be confused. I think you remember when we talk about that, because when the water is ionized, it's kind of firmly loosely bond. So we can write both the similar way. So we can write the HOAs, or even we can write this way, both are okay. Okay, so actually what happened here, first step, the mechanism, the protonation of double bond. So obviously here the bond break, and this proton, the pi bond break, and this proton go here. And here, when you know oxygen is also electronegative, so when this bond break, and this oxygen takes the lone pair and leaving here the carbocation as a electron deficient. In the second step, nucleophilic attack of water. Here actually this one, or if you even if you say that this one, actually nucleophile, and then attack the carbocation, and then this is make a bond. Okay, so this way is also okay, or even if you write the HOAs, this is also fine. So this is how it happens, and here one step addition. What one step addition, as I said that in an ionized form, they also be here like that, H3O. So that's why this hydrogen is deprotonated. This is, as I said, this is very loosely bounded. So this hydrogen deprotonated, and finally the water. So yeah. But this is just for understanding mechanism. But if we ask you the chemical reaction, you need to write the chemical reaction. But as I said that if we see the different types of addition, we will say that which will follow the Markovnikov, anti-Markovnikov, or which is we have the little bit of addition and new. So that's why I'm telling you that please practice. When you will practice, you know that what is the extra in this kind of addition. So it will be easier for you to remember and understand, because now we cannot memorize the chemical reaction as long as if we don't understand. If we understand, that we need to just practice. Orientation of hydration. This is the same thing. Follow the Markovnikov rules. So you need to find the carbon which is more stable or less stable. Less stable part will be at the hydrogen, and more stable part will go for the nucleophile attack, and then alcohol, OH in that case. You can see this is the major product, and this is not. Now there's something new that is possible when you do the homework or the recitation, I will suggest you, especially the recitation, they do the lots of good question. That's really important for the quiz or exam because they also take from the same Wiley and same set of questions or something. So you will see some a little bit of exception like this one. What is the exception? Focus there. Like here, if we have the methyl group and also the carbon, secondary carbon and tertiary carbon are adjacent to each other. In that case, the methyl group can be rearranged or shifted internally. So from secondary to tertiary to make more stable product. And this is possible. Okay, and when possible, this is called the rearrangement of methyl group or methyl shift, and when it happens, the catalyzed hydration in the presence of acid. So what happened here, you can look here that in this case, what we had, the double bond carbon, if you see this one and this one, what we see. So normally if we don't consider the rearrangement, so then what will happen here? Here the hydrogen will go here, carbon, carbon, yeah, CH3, this will, and there CH3, CH3, OH. See, this is the normal things. However, yeah, but when we have the methyl group, see here, methyl group, methyl group, methyl group. So here the OH should come, correct? Normally here the OH should come and here the hydrogen, correct? Because here was the carbon-carbon double bond. However, it can be shifted. Why it can be shifted? When the secondary and tertiary carbon are adjacent to each other, it is possible to shift the methyl or carbocations. As a result, the hydroxyl group normally supposed to be here, but it comes here because it makes the more stable carbocation, and then this methyl shift to the secondary. So that means that it's supposed to be make the carbocation is here, but since this is secondary adjacent to tertiary and tertiary can make the more stable carbocation, as a result the carbocation form and the methyl group shift here, and this is possible in the presence of the acid. Okay, this is the possible rearrangement in the presence of catalyst hydration, or catalyst mean in the presence of 50% acid or some other mainly acid catalyst. So this reaction, try to be remember that this is the special. And if we find, okay, not only this one, I have another example actually. Oh, okay, I didn't take my notebook here, but not only that, if you see this kind of example that you have an acid catalyst, then please look into the carbon, that if you have a secondary carbon and tertiary carbon nearby adjacent, then and when you will see the catalyst, then you need to follow this kind of shift. And you know, this exception kind of reaction are very famous as an exam material. Try to remember. Yeah, practice. Now we come here the oxymercuration or demercuration. This is the another kinds of reaction that happens with the alkene. Here, this kind of addition follow the Markovnikov rule. As I say that mostly follow the Markovnikov rule. So you just need to practice couple of times, then you will be master on that. So this is called the how to say mercury acetate, okay, OSC. So this is called the mercury acetate. So actually this is H and OH, but this is in the presence. This is the special type of, like this is the milder condition than the direct hydration. So direct hydration is not possible when we have this type of reaction. So if when alkene come to react with this type of mercuric acetate, so what happened in that case? In that case, first this kind of intermediate formed, and we need to use the another catalyst, this type of reduction that makes the this type of final product. So let's see, and this when this type of reaction come, they cannot do direct hydration, and that's why we need this kind of catalyst or in the presence of, and that's why they are telling that milder condition than the direct, and no arrangement or polymerization happen here. The reagent is mercury 2 acetate dissociate slightly to form this ion. Here I want to tell you, we till now saw the carbocation, correct? But here this kind, protonation, hydrogen ion or something. Here consider that this, here just consider in place of this one will form, okay? And oh, okay. So this is the electrophile that adds to the pi bond. Okay. So then the intermediate is a three-member ring called the mercurium ion. We will now show. And overall, the addition of water follow the Markovnikov rules. So this is kind of things that direct cannot be possible. That's why we need to take the this type of special. And here you can see actually this is and this is the same thing, okay? See, mercury 2 acetate, this one too, mercury 2 acetate. You can write like that AC, and also AC actually you can see the COCH3 acetate. Okay, so you can write like that or like that. So when first step, this kind of ion will be formed, and then it will follow the same. This is called, this type of ion will form, and this ion will make a bond here by breaking the pi bond here. So this kind of three ring, this type of mercurium ion will be formed, and then you know the OH that will come. This is hydration, so obviously in the presence of water. So here just remember that OH will come, and water will open this ring, and they will make like that. When the water will open, so this will be go here and the OH, and this will be called the organomolecular alcohol. Okay. Finally, this place will be replaced by proton. Where we got proton? You remember the water. So here the OH part add, and the hydrogen part proton that will be replaced here. And this is the product will come. So this is the special kind of, that direct cannot be happen. But if we need to do to proceed this kind of addition, then we need to follow this kind of steps. So first, we have this ion that will join to the pi bond and form intermediate mercurium ion, and then the water will open this ring, and the OH will attach, and eventually the hydrogen will replace this mercuric acetate, and finally we will find the organomercurial alcohol like that. This is the actually the final product. So in the demercuration, so this is called the mercuration and demercuration. So first the mercuration, and finally the demercuration by this agent, and hydrogen comes here. So in the demercuration reaction, a hydride furnished by the sodium borohydride replaces the mercuric acid. The overall reaction gives the Markovnikov products with hydroxyl group on the most substituted carbon. That means most stable carbon. Here we have example. Yeah, I think, oh, by the way, here I gave you something just to remember the oxidation and reduction. So maybe you remember the ionic compound or bond, for example, the sodium chloride, sodium donate electron and chlorine, the negative ion, accept the electron, and as a result, they can make themselves more stable in their outer shell and octet. Any question? Yes, Mark Camel. Yeah. Oh, okay. So, so you can see the sometimes maybe you will see the oxidation or reaction. So I just recall here if you see like that. We will also see in the next. So we have here one problem solving. This is one methyl cyclopentene, similar kind of reaction. First, they will make the uh, this type of bond, and they will break the pi bond, and they will make the intermediate. So let's see here, and they will make the three-member ring like that. See the close mercurium ion. See here the CH3 and the hydrogen. So here will be add the this ion. And then this kind of intermediate will come. And that I also wanted something to tell that you remember the chiral carbon. Normally, when any kind of reaction, we see the chiral carbon. Carbon means the which carbon attached to different group or carbon. This is the chiral. So not the similar kind of functional group or atom. In that case, actually, we will see the stereo chemistry like enantiomer, or you will see the OSS dash. Okay, because of those things. The cis trans, or some can be upside, some can be downside. So as a result, different types of cis or trans addition can be produced. So when you will see the dash or wedges, you know that here we have. Sorry, you have any question? Okay. So you will see the dash always, okay? So here also the same, the mercurium ion is formed, and this is the trans intermediate, and the reduction of intermediate gives the Markovnikov product. And finally, we will find the replacement of this by this addition. Hydrogen will add here. So practice here, okay? Practice here. And here, if you, okay, this is the another one. So here, show the intermediate and product the result of alkoxy mercuration demercuration using the methanol as a solvent. So here, the solvent will be methanol, so not water. So but the system is the same. So system is the same. So first it will come the intermediate, and the follow the Markovnikov, and then finally we need to use any kind of catalyst to replace the mercuric acetate, and then the hydrogen will go. And this is the kind of reduction, because here hydrogen is coming, correct? So that's why we have to follow the same pattern. So please practice it here. Now, hydroboration of alkene. Hydroboration. So you may think that this one will be something, and this is follow the anti-Markovnikov rules. And why this is neat? Because this is a kind of reaction that discovered by the doctor or scientist Brown to produce the anti-Markovnikov or syn stereochemistry. Syn means same side. When the same side, syn stereochemistry. We know that stereochemistry have a cis trans, and here there are two new terms, syn or anti. Syn means when the addition stereochemistry, but do the same side addition, and anti different. I mean, opposites are not the same side. So this is the syn stereochemistry and anti-Markovnikov orientation. Anti-Markovnikov orientation, we know that carbon with the highest hydrogen will go nucleophile, and carbon with the most substituent will go the hydrogen. Just flip of the Markovnikov. So you need to be remember first these things and how you can see and how it happens. Okay. So H.C. Brown from this university discovered that diboron adds. So this is actually hydroboration. This is called the B2H6 diboron to alkene with anti-Markovnikov orientation to form alkyl borans, which after oxidation gives the anti-Markovnikov alcohol. And he won the Nobel Prize in the 1979 for this work. I mean, for this kind of, he is a pioneer. Diboron, tetrahydrofuran. This one is tetrahydrofuran, and this is the diboron. They make this complex, and this is kind of a intermediate formed finally. Okay. So, diboron is a dimer of boron and is in equilibrium with a small amount of BH3. So, this is kind of product is come. Now, mechanism of hydroboration. Here, the mechanism. Let's look into here. If we look into here, the same as we know that it will be following the anti-Markovnikov. So you can see that this is the tertiary, this is the secondary. So according to the Markovnikov, here should be high protonation and here should be BH2. But this is the anti-Markovnikov, so it does did the flip. So here will be the BH2 and here will be the H eventually. Okay, this is the transition state and this is the final state, and this is not the correct. So boron adds to double bond in a single step, with the boron adding to less substituted carbon and hydrogen adding to more highly substituted carbon. So now if you look into, actually this is mainly the two things, but unless we do the practice, there are so many reactions, but if we know this the mechanism, that makes your life easy when you practice. Oxidation of alcohol. So if you have this type of compound and you need to do the oxidation, this in the presence of base, and also see the peroxide, as I said in the beginning, it will follow the anti-Markovnikov. So you need to be find the carbon, which one is secondary, which one is tertiary. This is the way it will follow. Stoichiometry of hydroboration. This is, the stoichiometry and also the balancing of chemical reaction, how many moles of reactants we need to produce, how many moles of product. This is kind of here the just example. We have the 3 moles of alkene can react with each mole of BH3. Stereochemistry of hydroboration. So whatever we saw, this is our stereochemistry. If we have a chiral carbon, you will see the dash or wedges, and this is the transition stress, and this is how it forms. So the trans-methyl, 85% trans-2-methyl cyclopentanol, and that means the some will be also minor, and the racemic mixture. Racemic mixture of enantiomer, you know, correct? That the mixture of the both, but here the trans, this amount will be the highest percent because it follow the syn addition and also the antimarconic. I think here. Here we have the another addition. Okay, syn and anti-syn. Okay, syn addition, same side. The hydroboration step adds hydrogen and the boron to the same side. Hydrogen and boron to the same side, not the cis trans. This is called the syn addition. When the boron is oxidized, the OH will keep the same stereochemical orientation. See, the same orientation when it is oxidized and replaced by. So how you would convert the 1-methyl cyclopentanone to 2-methyl cyclopentanone. So here you can see here the anti-Markovnikov. You have to follow, and then it will be trans product. So working backward, use hydroboration oxidation to form the 2-methyl cyclopentanol from 1. The use 1 and 2 above and below the reaction arrow indicates individual step in a 2-step. So see here was the H and here was the CH3. So first, see the different orientation, H and OH. So this is how we can change the orientation and the final product we can find. But this is the anti-Markovnikov. The 2-methyl cyclopentanone that results from the synthesis is the pure trans isomer. This stereochemical result is also, I also remember we discussed in this section, is the most substituted alkene that results from the dehydration of this pentanol. Here we go, dehydration. Yeah, this is the catalyst for the dehydration. Addition of halogen. Here, in case of the halogen, so two same, correct? Chlorine, bromine, iodine. So that means either 2 chlorine atom, 2 bromine atom, or 2 iodine. That makes the chlorine molecules, bromine molecules, or iodine or halogen molecules. So here what happened that first one halogen will be added according to the Markovnikov rule, and then one will be the leaving group. And this type of addition, normally the product from this is called the vicinal dihalide. This is a very famous functional group. This is called the vicinal dihalide. I remember I discussed a lot when I taught last in alkene chapter. So chlorine, bromine, and sometimes iodine add to double bond to form a vicinal dihalide. This is an anti-addition. See, syn addition, the same side. Anti-addition, the both side. I mean the first, if this is like this side down, another will be go to the opposite side. Okay, so this is you need to be remember. So what happened, the mechanism here? So nucleophile, see there are kind of this kind of, so one bromine will go to nucleophile, will work as a electrophile, and they will make bond and they will leave this bond and see the this with the lone pair as a leaving group. So this is how the another, you can see that if this is the OH, so we'll do the same. Another example, if this is this one, it will make like that and it will leave, and then they actually make this type of brominium ion. So first we'll go down, then we'll go up finally. actually. So this is kind of mechanism, the halogen addition. You can see here now. So first, this bond will break, and this will, as a electrophile. Oh, sorry. They will broke the pi bond and come here and make here. And here there will be the here what happened, the one unique things that compared to we study the carbocation, here will be halonium ion. This is called, see, the plus is here, halonium ion. And then finally this will attack to this carbon and add here, and then here this will work on here, and this will open this halonium ion, and they will make this bond here. So this is how this one and this mechanism of this the addition of halogen work. Okay, so finally, the I want to revise here that if there any nucleophile, it will work as electrophile, one bromine, and then another bromide ion as a nucleophile leaving. So when they will work, they will make actually this one kind of halonium ion in place of the carbonium ion deficient of electrons. So then this nucleophile will work here, open this bond, and they will make bond here. When they will make bond, and this is open, so when they will open here, look into here, when this bond will be breaking, because carbon is leaving this halogen, opening this bond, because carbon is making a new bond with this one. And what happen here, then it will, when it's breaking, it will have the lone pair, so this can nicely make the bond here. And this is how actually the vicinal dihalide form, the addition of halogen. And this is the similar kind of chlorine, bromine, or iodine. Obviously, they have a reactivity issue, so some do faster, even some exception that cannot do that. By the way, I want to tell you one term. I think the page, regioselectivity. I forgot to mention this term. Regio, in the beginning. Here we go. Since the hydrogen, since the protonation segment, protonation step, hydrogen or proton will add to the carbon with more hydrogen or less stable carbon, and this is selective. That's why this kind of reaction is called the regioselective reaction or regioselectivity. Okay, this one I forget to mention. Now let's go back to yeah, we are, yes, we are here. Stereochemistry of halogen addition. See, this is also the, if you look into the same kinds of things, they will follow the backside, okay? Not the sine addition, anti-addition, see? Anti-addition. So the both side addition. So let's see here. See here. So first, this will make this type of bond, and then you see the backside attack. So one will go actually here, and another will go here. If this was on the same side, it would be cis, correct? And if this kind of backside, this is the trans. And sometimes when we need this kind of product, that's why actually this kind of reaction discovered, okay? So this is the bromium ion, and this backside attack is stereochemistry of addition. Bromine test for unsaturation. This is actually, I think you are going to do the laboratory experiment for that. So sometimes, we do the unsaturation test and using the bromine, and this is called the bromine test, because if we have some alkene sample and we add bromine in carbon tetrachloride to the alkene, this type of color you will see, but the color quickly disappear as the bromine adds to double bond, and they start to reaction. So if there is no double bond, the brown color will remain. So I think you are going to do it in the laboratory, this one. Okay, so this is also called the unsaturation test. Formation of halohydrins. Halohydrin formation means the If halogen is added in the presence of water as a solvent, the halohydrine is formed. This halohydrine group is like that. So if this is X, we will say this is halohydrine. If this is chlorine, chlorohydrine. If this is bromine, bromohydrine. If this is iodine, iodohydrine. Okay, and this is also follow the Markovnikov addition. Where you need to remember what know what things see I sometimes mention here. So look into here. And this is the mechanism of halohydrine. Similar things. First we have this halonium ion, and the second we will have the backside attack and halohydrine. So finally we will have this halogen. Before we saw the um, uh, two halogen in backside attack, but here since this is in the presence of water solvent, so finally it will backside attack, and one halogen will be reflex but this hydroxyl ion, and this is the Markovnikov orientation, and this product will form here. Here we have the stereochemistry. So remember, when we have the stereochemistry, look into the carbon. They have the different group or chiral center. That's why they show the stereochemistry. Orientation of halohydrine formation. Look here at the distribution of the electron. Larger sigma partial charge on the more substituted carbon. So that means that here the distribution is unequal, sorry. And then this type of first it will the intermediate, and then the bond will be broken, and this type of final will be formed. So the more substituted carbon of the chloronium ion bears more positive charge than the less substituted carbon. You can see. This is also the Markovnikov product. Okay. You need to know, and then it will be easy for you to find. If the Markovnikov know, you know that where the protonation and where the other product negative or nucleophile is, which carbon is going to add. Here we have one more things. See, they mention here. Propose a mechanism for the reaction of 1-methyl cyclopentene with bromine water. Okay. Here we have the 1-methyl cyclopentene. This one, 1-methyl cyclopentene reacts with bromine to give the bromium ion. Similar way, attack by the water could occur at either the secondary carbon or the tertiary carbon of the bromium ion. So the attack can be on the both sides. Attack usually occurs at the more substituted carbon, which bears more positive charge. So it seems here. See the tertiary, correct? See, look into here. And as a result, the product is from the racemic mixture. Why? Because we are taking that attack can be where here, attack can be where tertiary. But maximum amount can be tertiary. But it can be both the mixture. So that's why the product can be the racemic mixture. That means the both kind of enantiomer. I think you have the remember the definition of enantiomer, which are mirror image. Mirror image means left hand will look right, and like now we have the selfie camera, like that. Oh, oh no, somebody came here. I didn't look into. Sorry. But so late, kicked out. I'm not sure for some reason. Here we have the another. Could you please check it out, because we have still couple of things to talk. Yeah. Check it out, okay? Similar way. Yeah. Catalytic hydrogenation of alkene. This is the one of the interesting thing. I still remember I described last semester. So If we need the catalytic hydrogenation because we have some industrial application of this reaction, for example, the platinum, palladium, or nickel, so this is a different kinds of hydrogenation. What happened? The hydrogen first adsorbed by this metal, and then this metal insert the pi bond, and then they broke this pi bond, and then the hydrogenation happened. The hydrogen adsorb on the metal side that then do the addition. So this is called the catalytic hydrogenation. So hydrogen can be added across the double bond in a process known as catalytic hydrogenation. The reaction only takes place if the catalyst is used, because hydrogen cannot do by himself. Hydrogen first adsorb on this metal surface. Okay. I think if you look into the book, they have a nice figure, I remember so far. Yeah, so this is kind of the metal surface, and then platinum, and then hydrogen is adsorbed here, then hydrogen is going. There is a nice story. If you are interested, you can look into that. And here, the extension of this addition, and this is kind of sine stereo. Sine means same side addition. And don't be panic to see the D. This is the what is say the isotope. Yeah, this is the isotope of water. Okay, water have the three kinds of ethane. Correct. Water have the three kinds of. Okay, here we go. Water have the three isotope. One is protium H, deuterium D, and tritium T. So here is the another isotope of hydrogen. I mean, I just drunk mistake. The hydrogen have three kinds of isotope. So here the deuterium isotope, and we need to do the hydrogenation. Okay, so the hydrogen and the alkene are adsorbed on the metal surface. Once adsorbed, the hydrogen insert across the same face of the double bond, and the reduced product is released from the metal. So the same principle, and this is kind of sine stereochemistry, since both hydrogen will add to the same side. So that will not be different types of enantiomer will come. This is the another example that called the Wilkinson catalyst. I need to finish today, but it seems I cannot today even finish. So maybe I have to be a little bit more faster. Anyway, so this is also the another example, but similar kinds of experiment, the same, but this reagent is different, and this is called Wilkinson's catalyst. By the way, what I just tried to say, the nice picture and how this pi bond get access and this adsorb hydrogen go here. This is the explanation of those reaction. The need for chiral catalyst. Why we need the chiral catalyst? When we need the specific kinds of enantiomer, like we need either the D or L enantiomer, that time we need the specific kinds of catalyst, especially chiral catalyst, who can make only one type of product. And this is one kind of you don't maybe need to know that same mechanism, but the major things that you need to know this example, because this is one of the L-dopamine that that can cross our blood-brain barrier, and that also used in the psychotic treatment. So this is the one of the example that this L enantiomer can cross and be transformed into another enantiomer is toxic to the patient. So this is the reason that we need to be synthesize only this kind of enantiomer, and as a result we need this kind of catalyst. We have apo-oxidation. Actually, the figure is same. This group is called the epoxy acid when we have this one. Okay, they also do the similarly. This is called the epoxide. This type of this type of intermediate, and then finally, see, this type of intermediate, and finally they will do the epoxide and the acid, and this is the mechanism how the double bond break, and this peroxy acid, this bond and this bond will be break, and here this kind of bond will be formed, and this is called the epoxide, and the remaining will be the acid. So here this is called the epooxidation. Here an alkene reacts with peroxy acid to form epoxide, also called oxyren. The most common peroxy acid used is metachloroperoxybenzoic acid. And the peroxy acid and the alkene react with each other in a one-step reaction to produce epoxide and the molecule of acid. This is just you need to know what type of reaction is do. And this is 812 stereochemistry of epoxidation. I want to finish today here. We have just 2-3 more from the next. I don't want to run faster, though we have already done. Here just couple of special reaction that alkene do. So next Friday I will do here, and we will move on to the chapter 9. So do you have any question here? You guys are fine?